All right, this is LeetCode 1061, lexicographically smallest equivalent string. This is the daily problem for June 5th, 2025. I'm going to make this video pretty quick because I just had to, I just lost like a 10-minute recording because my OBS was not working for some reason. I don't know why. There's a recurring glitch with it that it just randomly freezes during if I'm recording a video, so that's very annoying. But yeah, so I really don't want to talk through this all again. But basically, this problem is dealing with you have two strings, and each pair of characters in the strings represents an equivalency relation, and then you have this base string, and you want to find the you want to replace characters in this string based on those equivalency relations to find the lexicographically smallest equivalent string of this one. So the algorithm to use here is union find. So you have like directed graphs. In this case, you only have 26 total nodes. Since there's 26 letters in the alphabet, and so you start with this. You could basically just store it all in an array here, and then you have this recursive find function, which is just going to traverse the each directed graph, and it's going to do a path compression because we're going to set whatever element we're looking at. We're going to set it equal to the basically as deep as we can go, right? We're just going to do a recursive call, and so eventually that'll result in the representative element for that directed graph. So this will essentially compress. It'll flatten the graph essentially. So if instead of having like node 3 pointing to node 2 pointing to node 1, if you wanted to call find on node 3, you'd have to go to 2 and then you'd have to go to 1. So the better way to do it is to simply move this pointer like that. And so so essentially you're reducing the worst case time complexity from O of 26 to O of 1. If you had n number of nodes, this optimization would be a little more helpful, but since it's just the alphabet, I mean, it's something, right? So that's why we do that, and that's why we do this recursive call. And after we loop through, we're also just going to make one final pass on that array to make sure that it's flat. So we're just going to call find on every element. But so yeah, I mean the more important part of this problem is when we're looping through all pairs of characters S1 and S2, right? So which is what we're going to do here. And so we're basically just going to look at what those current characters map to. So we're going to traverse our directed graphs for each character. So we're just going to call find. And then we have to convert it to an index, and so if those are different, then we just set the larger one equal to the smaller one. So, I mean that's where the lexicographic nature of the problem comes into play. So ultimately, let's look at this example, right? All of these characters should map to A. And so what our root is going to look like is it's going to look like, O is going to point. So like whatever the O's index is going to point to 0. Whatever E's index is going to point to 0, and etc. So at the end, all we need to do is just loop through the base string and then add to a result string. Just call find and then just add that character. Just like do a final mapping and then return that result. So it's pretty efficient. In terms of time complexity, like I said, this, is going to be, O of 1 amortized. This here is going to be O of n, where n is the size of this input string, which these two are the same length. This is going to be O26, and then this is going to be O of M, where M is the size of base string. So overall, you're basically looking at O of N plus M, which is pretty much the best you can do for this problem. So yeah,